Calculus video 50, the mean value theorem for derivatives. Okay, so we have one of our named theorem here, the mean value theorem for derivatives. We're specifying here for derivatives because we'll also have a mean value theorem for integrals when we get there. So in this case, mean value theorem for derivatives, often abbreviated as MVT, mean value theorem. And when you think about the word mean here, you should be thinking about average, right? Kind of that mean meaning the average, or the average value theorem for derivatives. The average value theorem, or the mean value theorem for derivatives, says this. Go ahead and pause the video and draw the curve that we have here. So I have a curve, a function f, and on that curve I have 2 points. I have the point a, f of a, and I have the point b, f of b. The average slope between those 2 points, so if I were to draw a line between those 2 points, I would have a line segment that would have a slope. That slope, right, the slope of this line is the average slope. It's the slope of the secant line. The slope of the secant line is the average slope between those 2 points. We remember that to find the slope between 2 points, you do delta y over delta x, or y2 minus y1 over x2 minus x1. Well, delta y over delta x, the change in y over the change in x, the change in y, it went from f of a to f of b, so that the change there would be f of b minus f of a. That's the change in the y value. And the change in the x value, the horizontal change, would be the b minus a. And so we see that the average slope is the slope of the secant line is f of b minus f of a over b minus a. That should look very familiar to us when we started understanding what is a derivative, right? Way back when we took the slopes of the secant lines and we had the second point get closer and closer to the first point, right? Using that slope of the secant line each time. The mean value theorem says this. As long as your function f is continuous on that interval ab and differentiable on the open interval ab, meaning that you can take the derivative at every point in the interval a to b, there's no sharp points or things like that, okay? As long as the curve f, the function f, is continuous on ab and differentiable on ab with parentheses, we will get some value c in between a and b such that this happens. That average slope that we found there, the slope of the green secant line there will be a point somewhere in between where the slope of the tangent line and the slope of the secant line will be the same. That the slope of the tangent line and the slope of the secant line will be the same. And in fact, there will be at least one point at which this happens, right? And so what we're saying is there's going to be some value c down here in between a and b, such that at c f of c, right, at the point, let's do this, at the point c f of c, the slope of the tangent line and the slope of the secant line are the same. Now, how do you find the slope of a tangent line? Right? Slope of the tangent line, remember, is f prime of x, or in this case, f prime of c. This is the slope of the tangent line. The average slope, green here, is the slope of the secant line. That's this one here. That's given by f of b minus f of a over b minus a. And what we're saying is, as long as the function is nice, it's continuous between a and b, it's differential between a and b, there exists some c between a and b, such that the slope of the secant line is equal to the slope of the tangent line. That's the mean value theorem. Okay, here it is, nicely written out. Mean value theorem. If f is continuous on closed interval ab and differentiable on open interval ab, then there exists a c in the interval ab. So let me do the symbolism here. This symbol here looks, let me draw it bigger. This means an element of, That's kind of a weird shaped E for element. An element of. What we're saying is C is an element of the set AB. Or another way to think about that is C is in the interval AB. Okay. In other words, there's some C value between A and B. Start over here. If f is continuous on AB and differentiable on open interval AB, then there exists a C between A and B in the interval A to B, such that f prime of C, what we have there for f prime of C, that is the, let me see if I can color code this. That was orange. F prime of C, that is the slope of the tangent line at C, f of C, is equal to f of b minus f of a over b minus a, that is the slope of the secant line between a f of a and b f of b. Okay, where the slope of the tangent line is equal to the slope of the secant line. Where you have a particular point where the slope at that point is the same as the average slope. Hence, you have a point that's the same as the mean slope, the average slope, hence mean value theorem. Okay, we're saying that there exists a C here such that the slope at C, at CF of C, is the same as the average slope between the two endpoints. Mean value theorem. All right, let's try an example. Use the mean value theorem. Let me pause. If we're going to use the mean value theorem, we have to be able to say for certainty that the provisos in the theorem are true. We have to be able to say that, for example, f is continuous on AB. We have to show that that's true to be able to use the mean value theorem. We have to be able to say that f is differentiable on AB in order to use the mean value theorem. So those two things have to be shown, written out, in order to say we can use the MVT. So whatever function we have, we're going to have to say that it's continuous on AB and differentiable on AB. Otherwise, we can't use MVT. Okay, use the MVT to find C. We're going to actually find that C value. We're going to, what number is that? What number is that C value? We're going to find that C value such that f prime of C, the slope of the tangent line, is equal to f of b minus f of a over b minus a, the slope of the secant line, the average slope. For our function here, the function we're going to use is the cubed root of 2x minus 6 on the interval 3.5 to 7. Okay, let's get a picture of what's happening here. The cubed root of 2x minus 6. Let's not use orange. Cubed root of 2x minus 6. I'm not exactly sure what that looks like, but I'm going to guess it's something like this. Pretty close anyway. When x is 3, 2 times 3 is 6, minus 6 is 0, cubed root is 0, 0. So I'm pretty certain that here we have the point 3, 0. Now we actually are only looking at the interval for 3.5, that's here, 3.5 to 7. So we're looking at from here to here. That is the average slope. The slope in that black line there, that's like the average slope. What we're going to say is, as long as this function is continuous and differentiable, there's some point in between 3.5 and 7, not sure exactly where it is, maybe about right there, such that the slope of the tangent line is the same as the average slope. So we're going to try and find what is that C value, somewhere between 3.5 and 7. Okay. However, to use this, we first have to say that the function is continuous. Well, it's a cubed root function, and a cubed root function is continuous, as long as what's inside the cube is also continuous, which 2x minus 6 is. It's nicely differentiable Right? You could take the derivative of 2x minus 6 to the 1/3 power for every value of x. Almost every value of x. There's actually one that it won't work for. Right? So it's not differentiable everywhere. Think about the derivative of f of x. Or think about the slope here. There's one point on this curve where the slope is undefined. The point where the slope is undefined is right at 3, 0. If you remember, for a cubed root function, you get a vertical slope right there. The slope is undefined at that particular point. However, the point 3, 0 is not in the interval 3.5 to 7. We'd be in trouble if we were going from 2.5 to 7. We wouldn't be able to use the mean value theorem. But since we're going from 3.5 to 7, and 3, the x value of 3 is the only problem here for having an undefined derivative, we can see that from 3.5 to 7 on that particular interval, the function is differentiable. So, we have f is continuous. F is continuous on the interval 3.5 to 7. And we have that f is differentiable. Not everywhere, but it's differentiable on the interval open parentheses 3.5 to 7. Okay. Because we can say those two things, that means we can now use MVT. So, what do we mean by use MVT? MVT guarantees us that there is some C value between 3.5 and 7 such that this thing occurs. So, by the MVT, by the mean value theorem, we know that there exists a C in the interval, I'll use the notation from earlier, C in the interval 3.5 to 7, such that f prime of C is equal to f of B minus f of A over B minus A. We know that C value exists, so now let's try and find it. All right. Basically what we're going to do is we're going to get the right-hand side. What is that average slope? And then we're going to take the derivative and see if we can work through it. So let's start with this right-hand side. F of B minus f of A over B minus A. That is f of 7 minus f of 3.5, those are the endpoints, divided by 7 minus 3.5. That's the average slope. Our function, which I've forgotten by now, is cubed root of 2x minus 6. All right, so f of x, to remind myself, is the cubed root of 2x minus 6. What is f of 7? That's the cubed root of 2 times 7 minus 6. That's 14 minus 6. That's the cubed root of 8. That's 2. What is f of 3.5? That's the cubed root of 2 times 3.5 minus 6. That's the cubed root of 7 minus 6. That's the cubed root of 1, which is 1. All right, so this becomes f of 7 is 2, f of 3.5 is 1, over 7 minus 3.5. That's 1 over 3.5, or if you want to multiply both top and bottom by 2, 1 over 3.5, top and bottom by 2, is 2/7. So 2/7 is the average slope between 3.51 and 7.2. Between those 2 points, the average slope is 2/7. Go up to go over 7, or go up 1, go over 3.5. Either way you would look at it, the slope here is 2/7. Okay, by the mean value theorem, we are guaranteed that there exists C in the interval 3.5 to 7 such that f prime of C is equal to 2/7. Is equal to that average slope. In order to do this, we need to know what the derivative is. The original function, f of x, is the cubed root of 2x minus 6, otherwise known as 2x minus 6 to the 1/3. The derivative, f prime of x, is bring the 1/3 down, 2x minus 6 to the negative 2/3, right? 1/3 minus 1, negative 2/3, times the derivative of the inside, which is 2. Or that is 2 over 3 times the cubed root of 2x minus 6 squared. If you want to write it like that. Or leave it as 2x minus 6 to the 2/3 in the denominator. That's also fine. Or whichever way you think might be easiest. Okay, what we're saying is there exists a c such that f prime of c, so I'm going to use c's now instead of x's, that 2 over 3 times the cubed root of 2c minus 6, that the slope at c, the slope at c here, the f prime at c, is equal to 2/7. Okay, we can do this. We have a ratio on the left-hand side is equal to a ratio on the right-hand side. We can cross multiply. Also, they both have a 2 in the numerator. We can divide both sides by 2 first. Maybe I'll do that. Maybe I'll multiply by 1/2 over here, multiply by 1/2 over here. Cancel the 2, cancel the 2, cancel the 2, cancel the 2. So now I have 1 over 3 cubed root 2c minus 6 squared. I lost the squared up here, didn't I? Sure did. Is equal to 1/7. So you can cross multiply, or you can just do reciprocal, right? You can reciprocate both sides. It's going to come out the same. This is going to say that the 3 times the cubed root of 2c minus 6 squared is equal to 7. Okay, looks like it's not going to be a nice number. Let's keep going. Divide both sides by 3. Trying to solve for c here. Cancel, cancel. I get the cubed root. Let's just do this. Let's go 2c minus 6 to the 2/3. Maybe it's easier to write like that. Is equal to 7/3. Let's take both sides to the power of what? Well, to cancel out the 2/3, I want to do 3/2. 3/2 here. That becomes 1 as an exponent on the left-hand side. So now we have 2c minus 6 is 7/3 to the 3/2 power. All right. I think it's probably time to get a decimal here. 7/3 to the power of 3/2, or to the power of 1.5, if you will, is about 3.56. So we have 2c minus 6 is 3.56. Let's add 6. 2c is 9.56. Let's divide by 2, divide by 2. I'm getting 4.78 approximately. C is approximately 4.78. Okay, let's see if that makes sense in context of our drawing. We were here. What we're saying is that C value here is 4.78. 4.78. Okay, I would buy that at the function value up there at 4.78, that the slope would be the same as 2/7. I could believe that. It's at least between 3.5 and 7, so that's a good thing. And I think we've done it. We have used the mean value theorem to find the C value, in this case 4.78, such that f prime at 4.78, the slope of that, is equal to f of 7 minus f of 3.5 over 7 minus 3.5. In other words, both slopes should be 2/7.